Good morning. I'm very glad that you all showed up. When I looked at the agenda, I saw that this talk may have been sort of snowing under in the MPI topic for the next 2 days. But a little bit of history on this talk. At some point, I've been here quite a number of times, and I started to realize that the speakers assume terminology that you may not know. And that's the quickest way to lose it. You start being confused. So I propose, why don't you have a basic introduction into parallel computing, so all those terms that like Marc-André will use, I will use, Christian will use, are familiar. You have at least seen them once. And of course, the way that goes, when you complain, you get asked to do it. So I got asked to develop this talk, and this is the second time. I gave the first one last year. So I made some changes, fixed some bugs, and hopefully we're going to have some fun. That's the whole idea. Don't try to remember everything. It's just that I hope to start building up some understanding of parallel computing with you. And I have a promise. I will not ask any questions to the audience. I hate that. Just when I'm checking my email or trying to stay awake, there's a question. So I won't do that to you. I'll have one question at the beginning, just for my understanding and adapting to the material. Anybody here who has experience in parallel computing, one way or the other? Okay, some good. Well, then you can correct me or add to it. Please do. This topic could be much, much longer. I got an hour. We'll still need to negotiate the next time because I think I would like to have more. So let's get started. And again, feel free to jump in, even if it's late. It's like sometimes my latency is measured in hours, if not days. 3 days later, I realized what I should have asked. So don't be shy. Just ask. Let's make this sort of interactive. My name is Ruud van der Pas. I live in Holland, although I'm usually not there. I travel all over the world. I'm part of the Oracle Linux engineering organization. And unlike most parts of Oracle, we don't charge anything. Everything in our team, if you don't go upstream with whatever you do, you don't count. You actually get blamed for not going upstream. And so we're like a little island in that big Oracle. Oracle is a huge organization. And I'm part of the Linux engineering organization. My background a long, long time ago is in mathematics and physics, more mathematics than physics. I'm really bad at physics, but I survived. And after that, I joined the University of Utrecht. I ended up doing numerical analysis, and there's going to be one slide this morning that shows my past. And then I moved to a small startup company called Convex Computer. It was a little bit like what you see today with AI. At that time, you had one big vendor called Cray. Cray built the supercomputers, as they were called, and everybody wanted to have one, but nobody could pay for it. So you had all these small companies, and like our slogan was, what was it, like a tenth of the price and whatever. None of it was true, but the thing was, it was cheaper but fast. And Convex was one of them. None of them survived in any case. So then I moved to Silicon Graphics, or SGI, and then Sun Microsystems. And that's how I actually got involved here, because Aachen was one of the first HPC customers for Sun Microsystems. Currently, I'm in the Linux engineering organization. But already when I was at SGI, OpenMP was announced. And since then, I like it. And nothing is perfect. We'll talk about that after the MPI part. And nothing is perfect. But we'll try to give you a good feel of what it is about. And I'll come back on Thursday. So if you want to avoid me, don't show up on Thursday morning. But in general, I'm passionate about performance and OpenMP. Marc-André will teach you everything about MPI. I have some slides about MPI, and actually I'm quite friendly, so. Okay, let's get started. This talk is really a random collection of topics. They have one thing in common. They're all related to parallel computing, one way or the other, and I'll try to put things into perspective, of course. So when I was preparing this list, I thought that's like an endless list of things that I'm going to present. But my main goal is to help you understand what parallel computing is, because the hardest part about parallel computing, it's not whether you use MPI or OpenMP or POSIX threads or Java threads, it's thinking parallel, because we're not humans are not so used to thinking parallel. That's really the hardest part. You'll find that. And if you make a mistake, you'll have a bug in your code, and those are usually not easy to find. Then I'll talk the long laundry list of topics, all sorts of topics, and then a little bit about hardware, because we're using hardware, and then I switch back to the way we program those things, because they are of impact on the hardware. And I finally start building a presentation about mistakes made in parallel computing, because that happens too. Of course, I never make a mistake, but you might make one. What's parallel computing? And this is embarrassingly simple by design, because again, I want to build it up. I need to go to the supermarket, and this is my shopping list. I need to get bread, fruit, and milk. And this is how my supermarket has organized things, and what I do, I go and get my bread, I go and get my fruit, and I get my milk. Okay. Well, there's something interesting about this, because I could go to that supermarket again, and I could do that in a different order, but my basket is at the end, at the checkout, is the same. In other words, the order in which I do things does not impact the result. My basket is the same. And that's the key thing about parallel computing. You have to give up the notion of ordering. And again, like I said, that's hard for us. But the result should be the same. Otherwise, you have a bug in your code. So that's the analogy, is like you can do those, you can go to any way you like. There's one little thing I couldn't resist to put in. There is an optimal path in the supermarket. So that's a little fine-tuning. But in general, that's the idea. And let's go back to science and codes and algorithms. So here I have two simple expressions. I'm computing A and I'm computing C, and they're independent. As obvious as it may seem, I can compute C before A, and the outcome is still the same. That means there's no order in these two computations. That means they're independent. Well, if things are independent, I can do them at the same time, because the outcome should not matter. And that's how you get your parallelism. So parallelism is all about finding things in your application that are independent, whatever it is. And once it is independent, you can do them at the same time. That's the concept. But that's the goal. You're going to exploit the parallelism in your application, hopefully. And the goal is to reduce the time to solve a problem. You don't parallel, well, you can parallelize for the fun of it, it's actually fun, but the goal is to make things go faster. This is another optimization technique. But you're going to be more greedy. You're going to use more hardware. You're going to use more of the system, or maybe multiple systems. And then the goal is to make good use of that and make sure it still goes faster. And that's easier said than done. And some examples of those resources are, it could be the cores in your system, and I'm going to explain a little bit about cores in a minute. It could be in a whole system. You could have multiple systems, or even all the systems that are available. I mean, there's these huge, huge installations, and you have a pretty large installation here yourself. You could use all of it. The trick is to make good use of it. And one of those things that you need to be aware of is what's called parallel granularity. You can have parallelism at multiple levels. You can have it at the instruction level. It could be a bunch of program statements. As I was just showing, my computation of A and C is independent. That's an example of the second bullet here. Could be calls to functions or subroutines. They're completely independent, so you can do them in parallel. It could even be a larger part of your program. The best way to parallelize an application is first get started. Learn. Learn by trying and like, oh, well, that's cool, that's a little bit faster. But eventually what you'll probably find is that you need to redesign things. Like, wait a minute, now I know I should parallelize here at this level and not here because that's more efficient. But meanwhile, you've learned a lot. So instruction level parallelism, I wanted to mention it because you'll see it popping up here and there, not so much in this workshop, but in other places. Here's a little loop, and it's only 4 iterations, and it's computing A and C just as I did before, but now with arrays. So I have 4 long arrays. Well, what you can do, the compiler will take that and it will generate an instruction, a multiplication instruction. Let me use my tool, a multiplication instruction here and the add here. And if the hardware supports it, those can be done in parallel. those two instructions can go in parallel, and that's the lowest level of parallelism that you have. But it exists. It's quite common, actually. And it's fairly easy for compilers to find this for you, so that's great. So that's the instruction level parallelism that you may have heard about. That's the lowest level. There's another thing. When you take that loop and you write it out, you see that you do 4 multiplications and 4 additions. And hardware may or may not support what is called single instruction multiple data, SIMD, SIMD. You'll hear that in the OpenMP part. Christian will talk about that. And what it is, it will take that whole block and turn that into one instruction. So it's called vectorization. You do like an operation on an entire vector. And if the vector is longer, if this was more, it would chop it up in pieces for you. That's all done by the compiler. So this would give you 2 instructions, a vector multiplication and a vector addition, but it's all parallelism. This one will do 4 multiplications at the same time, or 4 additions. And if you really have a nice chip, it can do both at the same time as well. So that exists too. So that's all parallelism that you won't even see in a way, but that already happens. What we're going to talk about with MPI and OpenMP is at a much higher level in a way. So how do you parallelize an application? Well, first of all, you need to select a programming model. I'll get back to that in a short while. And you're here to get trained on MPI and OpenMP, but there are other choices. There's POSIX threads for shared memory. There's Java threads if you do Java. You pick whatever you like or what you need. And then you're going to use the features. It's like you get like a toolbox, but you need to use that toolbox to build your house. And the toolbox will tell you what you can do and what you can't do and what you may have to write yourself. Some like how many function calls in MPI now? 600 or 700 or so you got a very big toolbox. And the message is use that toolbox, because the idea is that somebody with a lot of knowledge has optimized that for you. So don't write your own. And what I would add, and you know who to blame if it doesn't work well. So don't reinvent the wheel if you don't have to. And that's sort of what you do. And then you have a parallel application, and if it works well, you will enjoy some improved performance. What are the challenges? Find the parallelism. You will find when you have like an application of 100,000 lines of code, where do you start? Don't start blindly parallelizing. Do that with some thought, and I'll say more about that in my talk on Thursday. For one thing, you focus on the part that takes most of the time. And there are tools out there that help you find that. Like, okay, this is taking 80% of my time. That's the part you should parallelize. Probably not much else matters. So that's step 1. And I'm saying that, and you may find that childish, but too often I see that people fail those basic steps, and then you run into problems later on. So obvious, make sure to get the correct answer. Well, you'll find out that's not always easy in parallel computing, certainly. And I'll say a little bit about that at the end. So you get it all, you got the parallelism in, you get the right results. And now you got to make it perform well. And the saying is, we say it scales well. It means you add resources like cores or systems, and you see continued improvements in the performance. And that's where a thing called Amdahl's law comes in. And as ugly as it is, it's still true. And I have to talk about that, and I'll do that right now. It's a great moment in time, 9:25 on Monday morning, Amdahl's law. But here's the situation. You measure how fast things go. You add resources like you add threads, and I haven't explained that yet, but I'll do so. You add resources, and you would hope it just goes faster and faster. In other words, the improvement is a linear function of whatever you use. So let's say you use 8 cores, and then you go to 16, you would expect twice as fast. And for a while, you may get that. But then at some point, it starts to go down. And if this is at 20,000 cores, I would not be so worried. If it's at 8, yeah, there's an issue. You're not using the hardware in the right way for some reason. And what's behind this is often, the first thing to check is a thing called Amdahl's law, causing this to move away from this curve. And it's very simple. I need to talk about serial time is the part you don't do any parallel computing. So you have your time, you decompose your time into two components, the parallel part and the non-parallel part, or serial part, that's what it's called. And what you're going to do, you're going to minimize that serial part. Why? Well, let me show you an example. Let's say your application needs 100 seconds to run, and 80% of that time can be parallelized. 80%, well, what does that mean? 80 seconds on 4 threads or 4 cores means 80 seconds are reduced to 20. But I still had the 20 seconds that I did not parallelize. So my total time is 40 seconds. So it drops from 100 seconds to 40, which is not bad at all. But it means your improvement is 2.5, not 4. And this is the most commonly asked question. I'm using all those threads, and I don't get the benefit. It's not 16 times faster using 16 threads. Most likely this is at least playing a role in it. It's the first thing to check. You can do a bit of, I wouldn't say science, but you can do a bit of math. And what you can do is you can formalize what I've just wrote down. I have a parallel component that's shown in yellow in my time and a non-parallel part. It's exactly the same as the example. Then the time on P threads, well, this part scaled, so that's divided by 4 or 8 or 16. And this one was not modified at all, because that was not parallel. So you get that expression shown on the right as a function of the fraction of how much you've parallelized and the number of cores or threads or whatever you're using. So it's a function depends on 2 variables. And then Amdahl's law says the following. The improvement or the speed up that you get is a function of the number of resources you used and a fraction. And this is the formula. It's a very simple formula in F and P. The problem is the shape is rather ugly. Because if you take this example that I just had, in my case, 80%, that means F is 0.8. I was using 4 threads. And what I see with that is my speed up of 2.5. That's exactly what Amdahl's law predicts. So that's what I have. And then you can make charts. And what I'm showing you here is the expected speed up as a function of the number of threads. Depending, so it's really a 3-dimensional chart, but I'm really bad at 3D charts, so I'm taking a 2D slice out of it. And what I see, in the ideal case, each time I add resources, it goes faster and faster. I have that linear 45-degree angle speed up, as we call it. That means F equals 1, 100%. Everything is parallel. Pretty much that doesn't really exist. But that's the ideal. The worst case is 0, nothing has been parallelized, and of course, no matter how many threads I throw at it, there's no benefit. I call that the sanity check. The real curve is in between. And that's a pretty ugly shape when you look at it. For example, when you have parallelized 50% of your application, you won't get more than 2x improvement, no matter how many threads you throw at it. You go to 80, that was my 80, even with that, I can't go beyond 4. Even 95%, you don't get 10x. Very depressing. You're allowed to leave the building now, but please come back, because it's the reality. But always look at the bright side of life. This is a good part. This shows that you don't have to do a very good job to see some speed up. And that's very encouraging. You'll see that, like, hey, cool, it's faster on 2 threads, 4. Yeah. But you also, this tells you, if you really want to take benefit of all the hardware that you have to work really hard. Another good thing is, I'm not talking about 95% of my code. I'm talking about 95% of the time. So you need to use a profiling tool, and there are several available, that will tell you, where do I spend 95% of my time? That could be distributed over 3, 4, 5 functions, but you know that's your target. That's what you're going to tackle. And then you also know if you want to go further, you have to tackle what's underneath. That's what Amdahl's law says. It's not pretty, but it's the way it is. So another thing that it shows that the part that you didn't parallelize will get you sooner than later. That was the serial part. What you want to do as a minimum is keep that serial part as fast as possible. Keep that as short as possible. And one way is, and I'll talk about that in a short while, reduce the parallel overhead. You can have a perfectly parallel program. Functionally, it's parallel, but the performance is going to be really bad because you have too many other things going on, too much overhead. And I'll show a bit of that. So, yeah, that's the way it is. I can't make it any better. So, a message: always pay attention to single thread performance. And what does that mean? Play a bit with your compiler and options, and see whether you can find some options that are giving you better performance. For a number of years, I was part of the compiler team at Sun Microsystems. I'm not a compiler person, but one thing you see is that there's hundreds of options on these compilers. Take whatever, Clang, LLVM, GCC, and it's really sad because the option means that the compiler engineer can't make up his or her mind. Otherwise, it wouldn't be an option. The word option means you get to be in charge and with the responsibility. So play a bit with options. Yeah, those man pages are really long, but it can really pay off to spend a bit of time and find some better options. You don't have to find all of them. That's like impossible. But don't just use what somebody else told you to use, unless it's the same application. To do a bit of checking there, spend a day, half a day on it, and you may find rewarding things to just improve that serial performance, and then you parallelize. Now's another thing, like, what do you think? If your program runs badly on a single core, what do you think will happen on 10 or 20 or more? You think it will magically go better? No, it'll actually go worse. And there's a very good reason for that. Usually these days, bad performance is caused by the memory system. The memory system is slower than the CPU. So if you wait all the time for that memory system to deliver your data, that's already bad. But what if you do that 10 times as much because you're using 10 cores now? You're just killing your memory system. So again, spend some time on that. There's usually no magic here. One little thing, I go to these conferences and sometimes you see, I call that scientific marketing. Some scientist tries to sell their algorithm and some natural feeling creeps in, because if they only show you scalability, you could be fooled, because a slow algorithm scales better. We see that all the time, because you mask the cost of the parallelization. So if somebody, just a warning, if somebody only gives scalability numbers, I wouldn't say don't trust them, but ask, what's the absolute time? Because it may be that's a really slow algorithm, but it scales so nicely. So just be careful. Okay, that was a little side comment. Let's get more specific on threads and multithreading. This was on my laptop, the process overview. And what you see here on those things like top and whatever, you see a column called threads. And what are they and why are they there? I've already dropped the word a couple of times. Now it's time to get a little bit more formal about it, because that word will be used a lot in the remainder. A thread is a bunch of instructions, like these multiplies and adds and whatever you have, and its own state. So it's more than just the instructions. For example, there's a thing called a program counter. The program counter keeps track of where you are in your program. And each thread has its own program counter, which is nice because it means they can execute independently, because they keep track themselves where they are. There's no overall program counter. So a thread is just a bunch of instructions with state, like the program counter. And they can execute independently. That's your software vehicle to implement the parallelism. And this is why an application that uses those threads is said to be multi-threaded. You use multiple threads. Each thread can execute independently, and that's how you implement your parallelism. And then you have the hardware, which is also called multi-threaded. A multi-threaded architecture has the hardware to actually give you a performance gain. You can run, on a single core system, you can run multiple threads, but you won't get any performance benefit. When you have multiple cores, multiple units, then you can actually expect a performance benefit. So that's a multi-threaded architecture. And a multi-threaded application manages the software threads. So let's go back to my example. I said I can do these two operations in parallel. That's true. The question is, how do you do that? Well, you take your programming model, and that depends on the programming model. You see, like, probably already, well, certainly this morning, Marc-André will show you in MPI how you create the magic, in a way, to make things run in parallel. And later in the week, you'll see how it's done with OpenMP, and you can do it with POSIX threads. That's what I call the software magic. Will create threads for you. It's sometimes misleading in MPI. They sometimes call it processes, but essentially it's an independent activity. And that's all done in the software. For example, when you use POSIX threads, there's a pthread create call. That's my software magic. And then you have your threads with the instructions, and then you run that on hardware, and there's no link between the two. Like I just said, you can run 4 threads on one core. You won't get performance benefits, but you can do it functionally. Like it's nice to test, for example. Also for debugging, if you want to know whether a problem is really related to parallel computing or something else, you just run it on a single core and you see what happens. So there's no link between those two, but normally you would like to run 4 threads on 4 units, of course. And when you do so, you're going to have to deal with parallel overhead. So it's not only to find the parallelism, it's also to make it efficient. And in parallel computing, there are 2 notions of time. And I mentioned that, I made this slide because too often I get asked about it. Somebody will say, well, the CPU time will increase. If you use like the bin time command, you will see that the user time will go up as you use multiple threads. The goal is to reduce the wall clock time, the time on your watch. So one will go up, the other one will go down. And that's the confusion. People say, well, how can that be? The time increases. The time increases because of what's called parallel overhead. So don't be alarmed. You will see that the total CPU time will go up. If you would be charged for cycles, you would pay more, your bill will be higher, and hopefully the benefit is reduced waiting time. That's the wall clock time or elapsed time. And that's one of the things is parallel overhead. So let me explain that. So it's not only about parallelization, it's about efficient parallelization, because otherwise you could be killed in your own overhead. And that happens. People do a job. Functionally, it's parallel, but there's too much other stuff going on that you can actually eliminate. But if you don't do that, then you won't have any benefit or not enough benefit. You're all scientists, I don't need to do this. The same in a picture. So I have my program, and let's say it runs in 100 seconds. That's my reference. In the ideal case, if I use like 4 cores, I can cut it in 4 pieces, and each piece will now take 25 seconds. That's the ideal case. That's the goal. We call that embarrassingly parallel. They start at the same time, they finish at the same time, and everything is really clean. That's sort of the goal. In reality, you have these orange blobs here. Because first of all, think about it. You take a non-parallel program. How do you get it to run in parallel? You have to change it. You have to add library calls and whatever, depending on the model, but something will have to change. That's extra cost you didn't have here. So that's why the first part I color-coded that orange, because you got to get started. You got to get your parallel program started. You have to create these processes or threads. And normally that's very small, but it's still there. It's still more than what you had here. And then in between, there could be communication. You'll hear a lot about communication the next 2 days, because that's what MPI is about. And that will take time. And that will all go into your bill and adds to your bill. And think about Amdahl's law, that goes on the wrong side of your bill. And you want to keep that to a minimum, and I'm sure Marc-André will talk about that. Another reason why a parallel program may not perform as expected is called load balancing. That often goes back to the algorithm. In the ideal case, all threads start and finish at the same time. That's great. But there are algorithms, and think about when you're working on a triangular matrix, and let's say you're working on the rows of the matrix, the top row is longest, has most of the work to do, whatever you want to do with it. Maybe you want to transpose it or whatever you want. The next one has one element less work to do, less work as you go through that matrix. So not at all this will happen. It's more likely you'll see something like this. This one will run longest because that was working on the top row of that matrix, and this one was working on the last element. It's finished first, so they all start waiting for each other. And that will just burn cycles in the CPU, will go on your bill, but you won't get any benefit because you're all waiting for the last one to come in. It's called load balancing. As I said, it's more part of your algorithm than anything else, and there are ways around it. You can change things the way things are scheduled. So it's not as, this may be your first observation, often you can do something about it. And here we are, numerical results. I couldn't resist. Because it actually happened. We're using floating point arithmetic, generally. And if you use integers, don't worry, they're precise. Floating point, no. Floating point is an approximation of the numbering system. It's almost never exact. It's always a rounding that happens. And as you may have remembered from your numerical analysis class, the order in which you do things can affect the final result. There are some horrible examples where at the end even the sign is wrong. I mean, you probably have all seen that in a class or whatever. Well, now you're going to do parallel computing. And I just said a while ago, the order is going to be different. So your floating point behavior, your round-off behavior is going to be different. And here's a simple example. Let's say I want to do this expression. Well, if I would do that in the traditional sequential way, I would first do B plus C, then I add D to it, and then E. That's the straightforward way of doing it. But if I have a parallel computer, I could break that up. I could do B and C. At the same time, I could do D and E, and then add those two results to get my final result. From an algebraic point of view, that's the same. Doesn't matter. From a numerical point of view, it is. The round-off behavior is different. Long story to tell you, don't worry if you run your program on multiple threads and the results are slightly different. That's one of those other common questions, like the numbers are different. The scary thing is it could be a bug in your program. And we don't have a good answer. As sort of parallel computing community, we don't have a good answer to that. And there's some operations that are very natural candidates for this kind of magic, like when you do a dot product, you can easily slice it up. And then you run it on 8 threads and on 16, and you will see the numerical results are maybe different, probably are. And just be alert of it. But don't exclude a bug, because that could be the case as well. Okay, hardware. It's important because we all use it. In the good old days, life was very simple. You had what was called a central processing unit, doing all the work, doing everything, and the data and the instructions were in that memory. Well, quite soon people found out that the memory was too slow, and what was done was fast buffer memory called the cache to speed up. This path is actually, I should change the slide, this is much faster than this part. So it's easier, quicker to get your data from the cache than from the main memory. And the trick is to keep things in your cache and not go to the main memory. That was the whole idea. It's an old idea, works very well. You can do that for data and instructions. On a system with multiple caches, you got to be careful though, because you have all those caches, and how do you keep them in a consistent state? Because your data will go through that system. And the system that does that, that's a topic in itself, is called cache coherence. And cache coherence is built into the design. It's part of the design of building a parallel computer. And what it does, it keeps track of changes in your data. That's by and large what it does. And how it does it, it's part of the design. That's called cache coherence, and the reason I bring it up is that we need it later on. And each element, each line, technically, has a state. And the state, if you need data in that line, the state will tell you whether you're allowed to do it. It could be clean, then you can just take it. If it's marked invalid, then as suggested in the name, you can't take it. You got to find it elsewhere. And that's one of the things that can slow you down. But it's called cache coherence, and the reason that I need it is because it makes very nice parallel programming, because you don't have to worry where things are, and you'll see examples of that in a very short while. But there's some sort of a price to pay. First in the design and also in the performance, you sometimes have to take that into account. Now, by the way, I have two advantages over you. I can't fall asleep, that will be quite remarkable, but I can also see your eyes, and I see a lot of glazing eyes. Don't worry, this is like a little bit of background information, but the word will be dropped a couple of times. So let's go back to that design. We have the caches, the CPU, and the memory. Now the question is, when you have many of those, how do you connect them together? How do you turn that into a parallel computer? And there are two fundamentally different approaches. One is where you start with that building block, and then you connect them to a memory. And let me see, I can't reach it. Then here you have the cache coherent bus. That's why I mentioned that. That makes it appear like one system to you, even though physically it's distributed. And that's why you need cache coherence in these kind of designs. It's used to be called SMP, symmetric multiprocessing. But there's another choice you can make. You take those units and you cluster them through a standard network. And people started doing that. They would take workstations and connect them together through Ethernet and say, this is my parallel computer. And it is. The software implications are very huge. You're in for a different programming model, but it works. You can treat it as a parallel computer. The thing is, this network does not have that cache coherence. So that's the fundamental difference between a multi-threaded architecture and a non-multi-threaded architecture. So it's called a cluster. And then people took it further, because what you see in this design, you see there's like a single memory and a single path. Well, that doesn't scale very much. So what was then done is that thing was split. The network was moved from here to top of the memories. And that makes it what's called a NUMA system, non-uniform memory access system. And the reason is scalability of performance. Because here you have a single path in a way to memory. As you have faster CPUs or more CPUs, you start starving those CPUs. With this, you add a node, you add bandwidth. But you fragment your memory. And this is why I mentioned the cache coherence. And the cache coherence hides that for you. You don't see that. You need some variable on that machine, you'll get it. And of course, there are performance implications that I'll talk about on Thursday. But technically, it just works. So, and just to make that easier, you call NVIDIA, and they happily stick GPUs in that thing as well. So yeah, these systems are really, really complex these days. But that's what we have, and that's what we need to program, and that's what this week is about, essentially. I should change this. I dropped the word too often already, the word core and multi-core, but now it's time to go into a little bit more detail. For a long time, everybody used the word CPU, central processing unit. And that thing was doing everything. Then people started putting multiple of those on a single chip. I was at Sun Microsystems when that happened, and we had no idea what the hardware guys had invented. And we as software people had to try to make sense out of it. It turned out to be a good idea, so that wasn't all that bad. And then we started calling those CPUs, we call cores, but they're by and large your working horse. The core will do all the work. It will process, it can do everything. Now, you have specialized hardware, that's a different thing, but essentially a core can process anything you give to it. Whether it's efficient or not, that's question 2. And that means that about 20 years ago, and Aachen was one of the first to buy one, was this one. 2 cores. Totally sort of symmetric design. That was the quickest way to do it. We took the UltraSpark 3, we could put 2 of them on a chip. Then marketing said we can't call it UltraSpark 3 anymore, it was called UltraSpark 4, and there you go. That was it. But it worked. It gave people more power for the same, roughly the same money. And that's what multi-core actually does. And since then, you have lots of multi-core systems. Everybody is almost doing multi-core. So, and let me see. Yep. Now I need to talk a bit about memory. That'll come back certainly on Thursday in my performance talk. So we have the core's doing all the work. We have the caches. What you'll find is that there's a data cache and an instruction cache that's closest to the CPU. It makes sense. Instructions behave very differently than data. You typically don't modify instructions. So you can if you want to. And for some applications, take an example, databases are notorious for jumping throughout everywhere. So you really want to have a large instruction cache for those applications. Graph analysis is the same. Some applications can really benefit to cache the instructions. And you have one for data. So they're specialized, they're optimized for their use. The unit of transfer in a system is actually not a single element, it's called a line. You always get more than you ask for. Let's say you're working on a vector and you need A0. Well, actually, you get a whole set of extra elements. You may get A0 to A7, you may get 8, or depending on the size of the line. So you always get more than you ask for, and that's because of cost. It's costly to move data in these machines. So the anticipation is that when the first one is expensive, well, maybe you're going to use A1, and that'll be cheap, because that's very close to your CPU. If you don't do that, then you got a performance problem. But that's why it is called cache lines, and that's the unit of transfer. Then you have a level 2 cache. This is called a unified cache. It has instructions and data. It's much larger. This is kilobyte. This is like a megabyte or more. So this is significantly larger. And so usually the coexistence of instructions and data is not a big issue. And then you have what is called last level cache. In this case, that's one that spans all the cores you may have in the system. And that's sort of, at that level, the memory hierarchy, and data will travel through that as you need it. And again, there's those lines. And for those of you interested, the size of the line is not always the same. It's optimized for where you are. Then you got the memory. That's where data all starts and ends in a way. And the rule of thumb is really easy. If you want to get good performance, you want to stay close to here. Because while the capacity increases, I mean kilobyte, megabyte, lots of megabytes, up to terabytes here, your speed will go down. So you really want to optimize your program to stay here, and that's part of that sequential optimization that I talked about earlier. Compilers are getting good at it, by the way. Those cores are not as simple as I just showed them. Some designs have additional hardware threads. Part of the design, some have it, some don't. And they're meant to deal with a nasty problem in your application. Many applications don't use the core all the time. You're waiting for something. Maybe for a cache miss. You need data. It's not in your cache. You got to get it from far away. It's called a cache miss. Maybe I/O. You're waiting to read from disk. Idea was, and that was based on a study, a paper, very influential paper. They found so many gaps in the execution across quite some applications that the hardware designers thought, you know what, we can do that. We can handle that. And here's the idea. Here I have no hardware threads. I'm executing my program. Let me see if I can do this. So you start here, you have the light blue, then you're finished, and you go to the dark blue, could be another process or another thread. But in between, you have those gaps. Again, could be waiting for a cache miss or anything else, some synchronization. Idea is, well, if you have two hardware threads, What you can do, in that gap, you schedule the other one. And that's all done in the hardware. The operating system doesn't even know about it. It just happens. So you need to have the hardware to make it happen. And the benefit is just saving time. That second one has a faster performance for free, in a way. So if you have them on your system, try to use them if you can, see if there's a benefit. In the design is, if you don't have these gaps, there won't be any benefit. That's a source of disappointment. People say, well, I used those threads and it didn't help. No, because you had the luxury of not having those gaps. Okay. But most often you have. So that's called hardware threads. So when you have a core, depending on the design, you may or may not have a bunch of extra hardware threads. It's the hardware support to do that very fast switching in a way. And the OS will assign a number to it. And what I'll show you on Thursday, you can control wherever your program is running. You can control it down to the hardware thread level, and sometimes that's what you want. Hopefully not, but if you want, you can do it. And that's called hardware threads. So by now, think about how complex the hardware is. We have these nodes, and this is like a single SMP node, a multi-core node. I may have hardware threads in it. Then I combine them. I put a cache coherent network on top of it. And then it's almost like when you're looking at galaxies, like you see a galaxy and, oh, wait a minute, there are many, many more, because these ones you can put into a network. And that's a hybrid system. And guess what? That is what you'll be using, I think. This is your system. So yeah, you have well, always look at the bright side of life. You have the choice. You can use like OpenMP, I'll answer that question up front, cannot go over the standard network. You can stay within the box, perfectly fine, but that's also where it stays. If you want to use more, MPI is definitely the way to go, because MPI allows you to go over the nodes, over the boxes. So you may end up using two programming models combined, or all MPI. Then we have the GPU to add to the fun of it. Very powerful. I won't say much about the GPU, but they live in their own world in a way, and they're extremely powerful. I'll have a little bit of that, but certainly in AI now, NVIDIA is making tons of money with selling GPUs in the AI market. I guess somebody will talk about the GPUs maybe on Friday and AI. Yeah, so Friday this will come back. Meanwhile, there has been, I'll speed up a bit because I'm running short. We've seen some sort of what I call silent revolution. And there's a very interesting company called ARM. I'm sure many of you have heard of it. They don't sell you a product. They sell you a design. And you build it. You figure out how to build it. And that turned out to be quite a successful idea. You can go to ARM and you say, this is what I want. And Apple did that. They try to hide it, but it's just an ARM processor. And you go to them and you work with them like, this is what I want, and ARM will come up with the design, and then you got to figure out how to actually build it. They don't do that for you. And this is why we have pretty sophisticated designs on ARM. And not so long ago, nobody thought that ARM was powerful enough to be used in HPC systems until, in particular, the Japanese told them wrong, because there's a very large HPC system in Tokyo called Fugaku that blowing away, still number 4 on the list, even after 5 years or so. So ARM is very competitive, very performance, and it has the advantage of the scale, because you'll find ARM designs in your cell phone, in your tablet, in your laptop, but also in HPC system. And I just thought I'll share a little thing. This is like a little background thing. You don't need that for PPCES. ARM has the idea of what we call big little, and my laptop is an example of that. You have two types of cores. You have the fat, heavy, energy-consuming cores for the heavy work, and then the light cores for everything else. They're typically connected through an L3 cache. and other things you have. And again, there we go, cache coherent interconnect. So that everything looks like one system, even though physically it's distributed. And these are examples. Fujitsu has one with 48 cores plus 4 support cores. So you can see that the heavy cores are 48 and 4 lightweight cores. There's a company called Ampere. They have 80 cores on a chip. So it's all shared memory. It's all single system in a way. Here's what that's in this laptop. Now what you see 4 efficiency cores, 8 performance cores. I have a 38 cores GPU, 30 or whatever. And you have a neural engine for AI, a media engine to watch your videos, and an image signal processor. So why do I show this? If you're here in this class, there's a whole world out there that's interested in parallel computing, because you need, if you want to master those monsters, you need a lot of software. So it's not only restricted anymore to the scientific world, like you need that. And that's really cool. Show you this, you can see like how active it is, but I'm going to skip that. So parallelism is everywhere. That's the message. In your phone, in your tablet, in your laptop, and of course the large HPC systems. But it's not only that anymore. Like Samsung is hiring, you hired a couple of friends of mine to work on parallel computing there. So think about it. Parallel programming models, back to the software. How do we program those monsters? Well, distributed memory, MPI. MPI means message passing interface. I have a couple of slides on it, but you'll hear so much about it that I'll keep it really short. Shared memory, you can use POSIX threads. Being around there is sort of a standard, quite popular still. You have OpenMP. You'll hear a lot about OpenMP, or if you do Java, you can use Java threads, for example. Unfortunately, there's no OpenMP for Python. I'll preempt that question, or any other, or Rust, or Perl. I wish that was different, and who knows in the future, but for now, yeah, OpenMP is restricted to C, C++, and Fortran. And as I just said, in a hybrid system, you can play with both if you want. So I'll say a little bit about shared memory and distributed memory, and that'll finish this talk. In a shared memory system, this is the logical model. What you have a pool of memory, and the threads can access. The threads can access any element in that memory, regardless of where it is. Don't think about hardware now. That's actually implemented through cache coherence. But it doesn't matter. We, as software developers, we know anything in that shared memory pool we can access. Yep. Oh, sorry. No, I thought you had a question. Then you also need private memory. Each thread has private memory because, let's say, a simple example, you have a loop, and you have the loop counter. You don't want to have the loop counter here because that means another thread will modify your loop counter. That's not a good idea. So you want to keep that to yourself. So it's very natural to have 2 types of memory. And that's also part of the learning curve. Learning OpenMP means you have to think about your variables in this way. But you'll see a lot of that later this week. Transparent access, as long as you do the declaration, so you share things through memory, through the shared pool. In OpenMP, there's an extension because OpenMP had to support accelerators. Accelerators, you'll learn more about that in Christian's talks. They have their own memory. So you add to the memory hierarchy, and you have to copy things in and out. And you run them on the processing units, and then you get them back through that memory, and then back to wherever you want it. So the memory model in OpenMP is a little bit more complicated than the single shared memory model. That's how you do those things. Okay. Now, a little bit, how does OpenMP work? OpenMP, you have your source code. You add controls. You add to it. And with that, you express the parallelism, and you'll hear all about that on Wednesday and Thursday. Then you take a compiler. The compiler has to understand those controls, and luckily they all do now. Sometimes you need like a special option to say, recognize that. So the compiler will take that, turn that into a parallel executable. You execute your program. You have some environment variables, a runtime library, and that will give you your parallel program. The key step is here. This is what you do. The rest is compiler and libraries. So that's your responsibility. And here's a very simple example. I have a loop of 10 iterations. All I need in this case is a single line, and you'll see this quite a lot later this week. It's a parallel for. So pragma OMP, it takes the shape, it has the syntax of a pragma. That's because of portability, so other compilers can ignore it if they like. Parallel for, and here I couldn't resist, although that's also the default. Here you see private I, so this loop counter is going to be private because I don't want other threads to modify my loop counter. The vector that I'm initializing is shared because they all need to be able to access it. And again, that's part of the learning curve. This is the very first OpenMP that you may have seen. You'll see a lot more of it. And then the compiler and the runtime system will do the rest of the magic for you. That's this one line. They'll split it for you, and they'll run it in parallel. But again, you'll see much more of that. On the other side, you have the distributed memory. In distributed memory, MPI, as an example, message passing interface, nothing is shared. You control what is shared. You want this thread to know what's happening there, you have to physically send that data over. That's the key characteristic of a message passing model. You pass the information yourself. And in a way, all the memory is private. The sharing is through the network switch. And here's a little example, a sort of hello world in MPI. And first of all, I need to declare, in this case, an array to get the status of my operations. Then this one, let me see. This one, init, initializes the MPI environment. That's a mandatory call. If you don't do that, then you have an illegal MPI program. Then the second one, MPI com rank, will return an identifier in variable me, so I know who I am. Everybody gets a different ID, handed out by the MPI system. Now I know who I am. That's stored in this variable. Why do I do that? Well, what I'm going to do in this example, I'm going to send a bunch of integers from one place to another. So I need to know where I am. If I'm 0, then I'm going to send. And what I'm going to send is a buffer of, this is an array, 10 elements long, of type MPI integer. It's going to send it to you. So I have to initialize you to some other number, like 1. So what it says here, 0 is sending to 1. I need to make the messages unique, so I give it a label, and I need to tell it where to communicate within. That's a communicator, and of course an error code. The key parts here are, if I'm 0, I'm going to send to you, and you is another number. In the same program, because that's how usually MPI works, if I'm 1, then I need to expect a receive, because 0 is sending to 1. So 1 is going to say, well, MPI receive here. Let me show it on the other screen. I have an MPI receive here. It's going to store it. This data is in a different memory space, but I give it the same name just to confuse people. It's 10 elements. It's an integer, and I expect it from him, because multiple people could be sending to me. But in this case, I want to get it from the right one. And the label has to match as well. So with the labels and the ideas, you can differentiate, like, what are you sending to whom? And then I have the finalize. That's a mandatory thing to finalize it. So what you see here is you get the ID, or it's called a rank. Not so much called a thread in MPI, it's called a rank. And if I'm 0, send 10 integers. If I'm 1, I'm going to receive 10 integers. And then I stop the environment. So at runtime, this is what happens. You start your program. So one of the things with MPI is you run on both nodes, the same program. So on both nodes, you run the same program, and this is what they'll execute. Most of the code is the same, but here, for example, it's going to send to you, and I'm going to get a receive from him. And you have to make that match with the labels and everything. So in this way, I have a connection. I'm sending 10 integers from one to another. That's essentially all there is to know about MPI. Marc-André can go home now, but he will spend a lot of time to get back to this. Okay, last slide is some mistakes. I just want to give a heads up. I'm sorry I'm running a little late. OpenMP, you could parallelize something that's not parallel. That's very obvious, but it happens. Same in MPI, of course. You got to make sure that it is independent. If it's not, you have a problem. In OpenMP, it's a thing you need to learn about that shared and private variables that I talked about. Again, you'll get your exercises and everything, but that's a new element in your life. Before this stuff, you didn't have to think about your variables in terms of sharing in private. In MPI, you have to look at the send-receive mismatch. Do I have the right connection set up? In OpenMP, you can have synchronization errors where things are getting out of sync and you get bad things. In MPI, you got to make sure that these message labels match up, because if they mess up, then you may be waiting for a message that never arrives. In OpenMP, there's data races. In MPI, you have multiple processes running on your whole system. What if one of those crashes because it runs out of memory, for example? That could be something that you need to take into account. Yeah, I'll do this very quickly because it will be mentioned later. It's called the data race. When you have the shared variable, I'll do this very quickly because you'll see more of it. You have a shared variable, every thread can modify it. Well, what if multiple threads try to modify the same thing at the same time with a different value? That's called the data race. And that's what this is. So when you write data in a shared memory system, you have to be careful that you're not overriding what somebody else has been writing. And if you don't do that, you have what is called a data race. And that's a part of shared memory programming. It has nothing to do with OpenMP. In P threads, you have the same. In Java threads, you have the same. As soon as you use shared memory, you have to take that into account. And I'll just show you an example. This is the formal definitions. I'll just show you in a simple example. I have a parallel block of code. This code, you got to believe me for now, is all executed by all the threads. And I put my variable n into the shared pool here. And n is going to get a value, it's going to get the thread ID. But different threads have different ideas. So what I'm doing here is I'm going to try to write different values into the same variable. There's only one copy of n, and that's called the data race. And that gives you silent data corruption. It's really hard to detect. Again, you'll hear more about it in the OpenMP part, but it's part of OpenMP has ways for you to avoid this, that this won't happen, but you have to do that yourself. You're in charge. It's called the data race. So, the value depends from run to run. So, why writing parallel programs? I hope I did not discourage you with all the bad stuff. It is fun to do. It's nice to see things happening in parallel. And yeah, there's pitfalls with it, but I hope you're going to enjoy it in the week to follow. So I would say with that, I'm going to finish. And remember, on the OpenMP side, if somebody says OpenMP doesn't scale, it means bad OpenMP doesn't scale. Good OpenMP scales. Thank you very much, and I'm sorry for running a little bit late. Again, I'll be around a part of the day, so if you have any questions or want to discuss more, I'll be more than happy to do so. Thank you.